Okay, so in the last lecture you may recall I introduced the concept of derivative at a point. So we said that the derivative of f at a was written as f prime of a, and it was defined to be equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. And so in the problems we looked at, we were given the value of a, so maybe a was 1. Then we would plug in a equals 1 here, calculate the derivative by computing this limit. Then if you got another problem with a different value of a, say a equals 2, you would go back to this step, plug in a equals 2 and do the calculation again. And you may recall some of those calculations were very long, tedious limit calculations. There was a lot we had to do. So it will be convenient if we didn't have to redo that calculation every single time we want to find the derivative at a different point. And so we can do this by thinking of the derivative not as a calculation at a specific point, but as a function. So we define the derivative of f by f prime of x equals the limit as h goes to 0 f of x plus h minus f of x all divided by h. So what's the difference between these two things? Well, in this one, a is a specific value that we plug in. So we plug in some number and then we do the calculation. Here, x is a variable, so we don't plug in any number for x yet when we go to calculate the derivative. So in particular, this thing depends on x, so the derivative is actually a function of x. So by leaving this thing in terms of x when we do our limit calculation, it means that later we can plug in any value of x that we want to get the value of the derivative at that point. So basically, if we want to change the point, we don't have to redo the calculation again and again. We just plug in different values of a to our final answer. So this is very useful, and it can save us a lot of work. By the way, just like we had for derivative at a point, there's an alternative notation using the Leibniz notation. We sometimes also write this is equal to df dx. So the df dx and f prime of x are two equivalent notations for the derivative of a function, and then the definition is through this limit of difference quotients. So I think it would be useful to do an example so we can really see how this works. So let's start with a relatively simple function that we've actually more or less done this for in the past. So find f prime of x if f of x equals x squared. So even though we have this x here, the method for doing the calculations is really very similar. So we say that f prime of x is equal to, by the definition, this limit as h goes to 0, f of x plus h minus f of x divided by h. Now we plug in what our function f is. It's x squared. So this is equal to x plus h squared minus x squared, all divided by h, limit as h approaches 0. Now if we expand the square, then we'll get limit as h approaches 0, x squared plus 2xh plus h squared minus x squared divided by h. And if you remember in the calculation that we did when we had a value that we were plugging in, we got a very similar expression where everything that didn't have an h in it canceled out. So basically we got exactly the same expression as before, except for now we have an x instead of whatever the value of a was. But we can still cancel these x squareds to simplify this to limit as h goes to 0, 2xh plus h squared over h. Cancel an h from everything to get limit as h goes to 0, 2x plus h. And then here we have x, which is a variable. We don't know what the value of that is at this point. But notice the limit only depends on h going to 0. So this 2x is not affected by the limit at all. It's like a constant with respect to this limit. And this h still goes to 0. So our final answer is just 2x. So notice that when we did calculation of derivative at a point, we got a number at the end. Now at the end of our calculation, we get a function which depends on x. But if you recall, I think in the last video I did the derivative of x squared at x equals 2. So if we wanted to know that now from this calculation, all we would have to do is plug in x equals 2, and you'd see that you get 4, just like before. So we can immediately say that f prime of 2 is equal to 2 times 2, which is 4. But now, if I asked you, okay, what's the derivative at x equals 7? We don't have to redo any of these calculations. We can just say that f prime of 7 is equal to 2 times 7, which is 14. So by doing the calculation in terms of x, we can really save ourselves a lot of time. And also, this has a lot of extra information in it. Before, we were just getting information about how quickly the function was changing at a single point. Now we get information about how the function is changing at every value of x. So this is a much more useful tool. So it's going to be very useful to be able to compute derivatives of functions. So I'd like to quickly go through a calculation of at least a few common types of functions that we're going to run into. And as we go through the semester, we'll find more and more ways to quickly calculate derivatives without going through all of these steps. But I'd first like to show you how to calculate the derivative of. So linear functions are pretty much the simplest functions around, other than constants, I guess. But constants are a special case of linear functions. And so these functions have the form f of x equals ax plus b. So a and b are constants, and x is our variable. So a and b are basically just fixed numbers, but I want to leave them as a and b so that we can apply the formula we get to any line, no matter what a and b happen to be for the specific example we have. And in particular, if we were to pick a equals 0, then that would give us the derivative of f of x is just equal to a constant b. So let's see how we can do this calculation. F prime of x is equal to the limit as h approaches 0, f of x plus h minus f of x, all divided by h. Let's plug in what f of x is. We get the limit as h goes to 0 of a times x plus h plus b. This is f of x plus h. Then we have minus ax minus b. This is the f of x piece. And we still divide by h. So now if we multiply out this a times x plus h and do some cancellations, we'll get limit as h approaches 0, ah divided by h. And now we can cancel the h's and we just get a, which was the slope of the line. So this sort of makes sense. If we have a straight line, we expect that it's going to just be going up with a constant speed. And indeed, that's what we get, that the speed at every single point, or the instantaneous rate of change at every single point, is just a. So it's a constant in this case. It does not depend on x. But the linear functions are the only ones where the derivative will be a constant. Okay, so this is convenient. Now, anytime you're given a line and asked to find the derivative, we do not have to go through this long limit calculation. We know the answer is always going to be the slope of the line. And as a special case, a equals 0, then f of x is a constant function. And by this calculation, f prime of x is equal to 0. This means that the value of the function is not changing, which makes sense because the function is a constant. And this is an important thing, so anytime you take the derivative of a constant, it's 0. So no matter what that constant looks like, if I take the derivative of 7, it's going to give us 0. If I take the derivative of 10,036, it's 0. If I take the derivative of 17 pi over 96, it's still 0. So later in the class, it will be important to keep this in mind. It's very easy to make these mistakes where you see some complicated expression like this, and you start worrying about what the derivative of it is, but the point is it's just some constant. No matter how complicated it looks, its derivative is always 0. So those are all the shortcuts I'm going to show you for now, the derivative of a linear function and the derivative of a constant, but we'll see more later on in the class. Okay, so now that we've seen some examples of how to calculate the derivative and what it actually looks like, I'd like to explain a bit more about what it means and what it can tell us. So let's look back at the example of f of x equals x squared. Well, we've already calculated the f prime of x is equal to 2x. That's what we did in this first example here. So let's plot these two functions on the same set of axes. So let me get a color here. First, I'll plot the function f of x equals x squared. So that's a parabola, something like this. So now I'm going to plot the function f of x equals 2x. Hopefully the color shows up on the scanner. I'm doing this in green. And this will be f of x equals 2x. Or I should say, yes, f prime of x equals 2x. So this is a separate function. So we can plot the graph of that as well. And now I'd like to examine some things about the relationship between the graph of the original function and the graph of the derivative. So let's first look at when x is greater than 0. So f prime of x is equal to 2x. So if x is a positive number, then the derivative will also be positive. And so this means that the function should be increasing based on what we discussed in the previous lecture. And we can see that also here. Everywhere over here where the green line is above the x-axis, we see that the function is going upwards. When x is less than 0, f prime of x is negative, right? That's over here. And we can also see that the function is going down when the derivative is negative. And lastly, at 0, we have that the derivative is equal to 0, and the function there sort of levels off. There's a horizontal tangent line, and it's neither increasing or decreasing at 0. It's flat. So just based on drawing this green line here, we can sort of predict how the function f of x is behaving. And this is true in general. So whenever f prime is greater than 0, f is increasing. Whenever f prime is less than 0, f is decreasing. And whenever f prime equals 0, we have the maybe I should say the graph of f is flat, or f is neither increasing nor decreasing. So this is another advantage of the derivative function. When we calculated the derivative at a point, we got all this information at a single point, but now we have this information for the entire function. We can tell from the graph of the derivative when the function is increasing or decreasing at all points. All right, so the next thing I want to discuss is that, okay, we're going to be spending a lot more time on how to calculate derivatives, so we'll see how to calculate derivatives of basically all the common functions you're likely to run across. But for the moment, there are still some derivatives that might be difficult to calculate, or maybe we're not given all the information about the function. So it's important to be able to approximate derivatives. Using difference quotients. So the idea here is that the derivative is going to be equal to the limit as h goes to 0, f of x plus h minus f of x divided by h. And as long as the function is nice, like let's say it's continuous, let me not say too much more specifically about what I mean by that. Just let's assume that nothing crazy happens with this function f of x. It sort of is like this nice looking parabola. It's a graph that we're sort of familiar with. Nothing weird happens. It's not one of these crazy examples like I showed you towards the beginning of class where limits didn't exist or things like that. So everything is nice. Then we've seen that to find the value of the limit, what we can do is plug in just a small value of h and see what the value of the difference quotient is. So if we plug in h equals, say, 0.000001 and then see what value we get, then it's reasonable to expect it might be close to the value of the limit of this function. So again, there are problems with this because we don't know for sure, for example, how small an h value we need to plug in to get close to the actual value of this limit. But let's just assume that's not a problem for now. So we can approximate the derivative using this. So let's see an example of how this would work. So suppose that the values of our function are given in a table, so we don't know the values at every point, but just at a few of them. So let's suppose we have x and f of x, and I'll just make up some random values for this function. Let's say 2, 2.1. Okay, and let's suppose we want to find the derivative at x equals 1.3. So we can't actually find the derivative exactly because we don't have much information about the function. We just have a few values of it. We don't have a formula or anything like that. But we can estimate the value of the derivative in a few different ways. One is using what's called a forward difference. So in this case, we'd look at the difference quotient, f of x plus h minus f of x divided by h. And we only have information about x equals 1.3, x equals 1.4, and x equals 1.2 for the values near 1.3. So a good value of h to pick would be 0.1 because we have values within a distance of 0.1 on either side of the value we're interested in. So let's pick h equals 0.1 and see what we get. So f of x plus h in that case would be f of 1.3 plus 0.1, which is this value here. So we have 2.1. Then f of x is just f of 1.3, so that gives us minus 2 divided by 0.1. This gives us 0.1 divided by 0.1, which equals 1. So we could say, based on this calculation, that f prime of 1.3 is approximately equal to 1. That's our best guess using this forward difference method. But remember, for a limit, it's important to look at both sides. So we could also use what's called a backward difference. Which looks at f of x plus h minus f of x over h. But now we take h equals negative 0.1 so that we get these 2 points, 1.3 and a point to the left of 1.3. So with this value of h, we have f of 1.2 minus f of 1.3 divided by negative 0.1. And if we look back up at our table, we have 1 minus 2 all divided by negative 0.1, which, if we simplify this, is equal to 10. So using the backward difference method, we would say that f prime of 1.3 is approximately equal to 10. So you might say, well, this isn't very good. Using one method, we got an approximation of 1. Using another method, we got an approximation of 10. That's really not so great. But we also have very limited information about this function, so this is the best we can do. We pick one of these estimates and say, okay, that's what we think the derivative is. We can do slightly better than this if we average these two estimates together. So a slightly better estimate is if we take the forward difference estimate plus the backward difference estimate and divide by 2, which would give us 11 divided by 2. But again, all of these three are reasonable estimates for what the derivative is at 1.3. And the reason they're all very different is just because we have very limited information about what the function is actually doing near 1.3. So this is the best that we can do. Okay, so in the next lecture we'll be learning more about how to interpret derivatives. But that's it for today.